Okay, so we'll start the talk now. So greetings, everyone. It is my pleasure to introduce Dr. Hakan Toreyin to the Computational Science Colloquium. Dr. Toreyin is an assistant professor in the Department of Electrical and Computer Engineering here at San Diego State. He received the BS degree in Electrical and Electronics Engineering from Middle East Technical University in Ankara, Turkey, and in 2007, and his master's and doctoral degrees in electrical and computer engineering from Georgia Institute of Technology. Dr. Toreyin was a Fulbright scholar during his Master of Science studies and received the award in 2012. Dr. Toreyin is currently associate editor of IEEE Journal of Translational Engineering in Health and Medicine, and the IEEE Transactions on Biomedical Circuits and Systems. Today's title is Energy Efficient Physical Computing Approaches in Biosignal Processing and Hardware Accelerators. Please join me in welcoming Dr. Toreyin.
Thank you, Dr. Paolini. And also, I'd like to thank you and Dr. Castillo for hosting me, for inviting me, for giving a talk, and providing me with this opportunity to introduce my research to a larger, greater community at San Diego State. Yeah, like the title of my research topic is actually, my talk is covering part of my research focus, and it's particularly on energy efficient physical computing. And I'm particularly interested in processing biosignals. And as a current interest and towards like more future interest, I'm interested in hardware accelerators, applying the energy efficient physical computing on those. So my talk today will be on both of those. So like to give you some idea about the motivation behind my research of physical computing is if we consider wireless sensor networks, we can think about different types of WSNs, terrestrial, underground, underwater, mobile, multimedia, with different applications in mind, like smart grids, industrial applications, agriculture, military, entertainment, medical applications, and so forth. So the idea about these wireless sensor networks is we are talking about distributed and many numbers of sensing nodes distributed across some field, and that field can be can have easy access to resources, like if the sensor nodes are, for instance, in a facility or in a factory or in a home environment, we are not worried too much about like the power consumption of those sensor nodes. But in certain applications, we are really like distributing those sensors here, like underwater with some batteries. So we expect those sensors to collect data and transmit the collected data to eventually cloud through some middleware like gateway, and where the large amounts of data are going to be processed. So in this scheme, like in this, you see like an example sensor node distribution. So each of these sensor devices, like an example sensor device, as you see, is able to collect some sort of data, whatever that is, we don't know, but that data needs to be transmitted to cloud. And usually like this gateway middleware is used to collect like clusters of sensors data, and then which is transferred to cloud later on. And the problem here is like if particularly these sensor devices are battery operated, then it's going to be needed that this sensor node can only send data maybe like every once in 24 hours, or even maybe rare than that, so that it can last, like its battery of, like we are talking about pretty large batteries, can last for maybe like years. But still, like in certain applications, the years amount of time is not enough. Like we would like them to last, like those sensor nodes to last longer than years. And an example is body area networks. So like now our body is where these sensors are, or those nodes in general are distributed. And although like in this figure, where I got this figure from, shows all of these sensors, like some of those at least, as like variable sensors, such as inertial sensor node, EMG sensor node, blood pressure, ECG. So those can be easily variable. They can be built in a variable form factor. So that means that you have the access to replace the battery. But the thing is, like in certain critical patient monitoring conditions, where let's say like you have a history of a heart attack, and then your cardiac rhythm needs to be monitored continuously, and so in that case, you instead of like having an ECG sensor with electrodes attached on you all the time, you would want some injectable ECG monitor, maybe, such as the ones that Medtronic is building. And in that case, like you're basically placing your sensor node right under the skin. And in that case, the problem is you cannot go with the same large batteries as you would go like for the wearable sensors. So the injectable device is significantly smaller. It needs to be significantly smaller than the wearable. The advantage of it is it gives you the user to like not worry about it at all, and also like it gives the advantage of eliminating the skin, giving or degrading the ECG signal or whatever signal that is being collected. So like we get rid of those. So like we usually get a better signal to noise ratio signal, but that comes at the cost of like the lower battery. And when I say lower battery, like the battery capacity goes from milliamps hours of capacity for variable nodes to nanoamps hours battery capacity for injectable. So, but the idea is like maybe we are still early in that process, but like in the future, in the near future, we expect to have a bunch of nodes around our body, continuously monitoring our performance, our health status, and that those can communicate with like a smartphone like this, where the data eventually is sent to the healthcare server for the physician's attention, and etc. So my focus is like to make these sensor nodes intelligent, so that they do not continuously send the raw data. They don't send, for instance, ECG signal continuously, but instead it sends it only like when there is an important event. So what might be considered as an event, of course, is dependent on the context. Let's say like an arrhythmia event, when it is detected on chip, only then the ECG recording will be maybe like sent for a certain amount of time, or like some predictive processing can be performed. So like in the event that there is a potential arrhythmia is going to happen, when at that time only like the sensor start sending out the data to the smartphone. So this way, by operating the radio, the transmitter, only like by waking it up only at certain times, you can significantly extend the battery usage, battery lifetime. So when I say radio, like we're talking about really like the best power efficient radio is like burning tens of microwatts of power. Considering the nanowatts of power, that radio should be really operated only like at rare events. So another advantage of Aside from that, improving the power performance of a sensor node, another advantage of doing like adding some intelligence to these nodes would be transmitting only physiologically relevant information. At the end of the day, the clinician would want to see, is not too much interested in like these portions. It's more interested in like certain features out of an ECG signal. Like I'm only showing one of those features, but we have also a P wave, a QRS wave, as I'm showing, and T wave, and their durations and etc. So like those things are important. So rather than sending out the whole thing, like the noisy portion, like the portion that is not so much interesting to the clinician, only like those portions important can be maybe digitized or sampled at greater rates. So a brain node needs to be like in taking can take some part in deciding on those things. Another thing that such a brain node adding intelligence to those sensor nodes would be in a future scenario, like I'm showing here a vagal nerve stimulation node. Like this vagal nerve stimulation is a treatment method currently used, and it's for it's an electrical neuromodulation where the neural activity is controlled, modulated by electrical pulses. And by doing so, by targeting this vagus nerve particularly, what is achieved is like the autonomic nervous system health is enhanced. So like autonomic regulation of the person is enhanced. So the current way of doing this is, well, a few years ago, the current method was doing this in an open loop manner, like the pulses like delivered to the neurons or nerve, the vagal nerve is preset. And however, now like these days, what is done is these pulses are controlled in a closed loop manner, where the closed loop, the loop is closed based on the feedback from certain signals, physiological signals that tell about the autonomic nervous system activity, such as heart rate variability. So heart rate variability is something that this ECG sensor node can extract and directly deliver, just like the heartbeats. And this vagal nerve stimulation node, when it is like when it is injected, like sitting right next to the vagal nerve, can deliver the heartbeats every second, or whatever your heart rate is, and then it will decide on what amplitude or what frequency the nerve stimulation should be conducted at. And in this way, we are definitely bypassing an external processor, and we are not adding burden on the too much burden on the radio. We are not increasing the power consumption of this. We are making the radio to just send one pulse, not like raw data of like 8 bits, 12 bits at 250 hertz or whatsoever, but just one beat per 1 second, like let's say for 60 beats per minute of heartbeat. Heart rate. So like this monitoring of ECG can be combined with the treatment of the vagal nerve stimulation by the help of this brain node. And lastly, like this adding intelligence to the sensor node is also helpful in the sense that we are currently like a variable system measures some physiological signal, and it sends the data, and then when we process it offline, we see that, okay, some part of the data is not really good, like the SNR is not good, so like it's kind of waste of data transmission. But some intelligence can tell if the SNR is enough, sufficiently good or not, and many of these sensor systems have some knob or 1 or 2 knobs, or at least, that can improve the SNR, or that can adapt the SNR, or keep the SNR at a certain level by adding some amplification, or by adding some, if we are talking about some active sensing, such as pulse oximeters, like we can increase the light intensity that is shed onto the skin so that we can collect greater amount of a greater amplitude of signal. So we can ensure that high SNR with the help of such a brain node. So the loop is still closed, but for the sake of this time, just the monitoring system as well. So in that case, if this brain node needs to be implemented, of course, we need to be careful about how much power consumption that brain node is going to add on to the system. It definitely needs to be less than the radio power consumption, but it needs to be really significantly smaller than that. So in that case, physical computation can be helpful. So if I look at this power efficiency scaling from a 2013 study that compares digital computation against a biological neuron and analog computation. And we see that with the consumption of 1 milliwatts, digital in general, of course, this can be greater or less, but 10 millions multiply and accumulate operations per second can be achieved in digital, whereas in analog, the power consumption goes by 3 orders of magnitude less. For the same amount of computation, we burn 1 microwatt of power. A biological neuron, on the other hand, does it by burning 1 picowatts of power. I mean, it's actually 1/10 of that amount of calculations. 1 million max per second is performed by burning 1 picowatt of power. So analog computation has been out there. Actually, it's been out there before digital computation came in. But now, more recently, neuromorphic techniques, borrowing ideas from the brain or nervous system and incorporating those can potentially fill in this gap between analog and biological neuron. And I'd like to talk about this a little bit more later on, but to give you an idea about why digital and analog can be so much different in terms of power consumption. Here you see a digital adder implementation with all these logic gates. And you see here an analog adder implementation. What you do is basically bring together your currents I1 and I2 at a KCL node, and physically the current leaving the node is going to be equal to the sum of these two currents. So you are not burning any additional power. You are not implementing any active device. You are basically taking advantage of physical rules. Of course, analog adder is not going to be as precise as digital adder, but not for, if our precision target is, let's say, 12 bits or 14 bits or 16 bits even, for those cases, digital adder is going to need to be preferred if your resolution needs to be very small. But for effective number of bits of 6 bits, 8 bits, or 10 bits even, you would not be, analog adder will provide you the more power efficient solution and also more simplistic solution in general. So I made of that idea, and in a study that we've been working on with my PhD student, and we applied analog signal processing, analog computation on detecting real-time detection of QRS waveforms on ECG signals. And we based our electronics, custom electronics, on an algorithm, a famous algorithm. This Pan-Tompkins algorithm is in 1985 algorithm. It's famous. It's one of the simpler algorithms, digital algorithms, and it's one of the better performing algorithms in terms of detection sensitivity of even noisy ECG waves, ECG signals. And it's actually making use of those 3 things. One, it's making use of the fact that the QRS waveform is tall. The second is QRS waveform slope is sharp. And third, the QRS waveform pulse width is short. So like it's basically performing first a typical bandpass filtering to eliminate high frequency noise and low frequency swing, but it basically performs this differentiation to enhance this second property. It performs squaring to enhance this high tall waveforms, or like to take advantage of that QRS is tall compared to the others. And then moving window integration with certain window size to take advantage of this like short window of QRS waveform. And then eventually it does some adaptive thresholding, which we are not doing for the sake of reducing the complexity. But all of those operations, differentiation, squaring, and moving window integration, they can all be done in analog, and that's what we are doing. And this is basically our chip photo, like it's implemented in TSMC CMOS 65 nanometer technology, and it consumes like, I mean, its area is like 465 by 200 micrometer. This whole die is 1 by 1 millimeter by 1 millimeter. And we see like when we test our processor chip on an extensive amount of data. So here you see like a bunch of different waveforms at different steps of the algorithm, but at the output you see like those QRS waveforms are enhanced like this. And this is basically showing like all of the data sets. I mean, it's a common data set used for benchmarking algorithms, the QRS detection algorithms, MIT BIH ECG arrhythmia database consisting of half-hour recordings, 48 of those. So our sensitivity is 99.6% with positive predictivity of 99.4. And our power consumption is 1.2 nanowatts of power. So, and we are comparing this against a bunch of algorithms. Like you see, ours is Penn-Tompkins based. So like we have Penn-Tompkins based digital. You see like at least 3 orders of magnitude greater power consumption. Same technology, but much more power consumption. So we have here, we see like some nanowatts power consumption solutions. This is a simulated study. So like the performance values can change maybe like when they are implemented. But as what is common in all of these is like we have some analog implementation. So the algorithms implemented in 27 and 28 basically they do not provide any performance. So we can achieve the lowest, even in that case, like we achieve the lowest power consuming QRS detector in real time. And that power consumption comes from the fact that one of the things is we are processing primarily current type of signals. And these currents, like you see, like differentiator output is a current, squaring block produces a current. So those currents, will keep them in the orders of less than nanoamps. So like we are biasing all these amplifiers with nanoamps of currents or less than nanoamp, a few hundred picoamps of currents, and still can implement those functions. And what we are doing additionally, what makes this analog computation power efficient is when an ECG sensor, which is basically 3 electrodes, if we are considering one channel. So 3 electrodes producing like an input to a differential input as ECG, and that's an analog signal already. We are not adding any digitization here. We are not doing any A to D converter, and therefore there is no A to D converter. That usually also adds some around 1 microwatt of at least power onto the total power of the system. So that's basically one example of using analog signal processing for those body sensor network nodes potentially. And like I said, this algorithm was based on some early algorithm, Penn-Tompkins 1985 algorithm. And another research that I'm currently working on is like in the past 1.5 years I've been working on this, is I'm basically developing my own algorithm, like not my own algorithm, but some algorithm that has physical roots or nature roots. Rather than like in real world, like the signals and like information is, it's safe to say that like information is analog, and therefore a lot of processing is achieved in physically. So like borrowing some ideas from those physical computation principles and incorporating them or applying them onto some the problems that I pick is another type of research that I do. And with the hopes of course, eventually, as I'll show you in one slide, with the hopes of implementing a originally digital algorithm in analog can be or cannot be easy. In this case, it was. We were able to do that, like with my student. But if we go with a physical computation, hopefully, like it should be relatively more straightforward. So that's the idea. And in that regard, I have come across this stochastic resonance phenomenon, where the noise, the background noise, environmental noise, is used towards improving the signal-to-noise ratio, counterintuitively. Like detectability of a signal is being improved, but with addition of some level of noise. So like that's the idea. And to describe this, to show it, this figure helps a lot. And what you see here is like our detector is simply, let's assume it's a threshold detector. And let's say like our input is a subthreshold. This is a sine wave, subthreshold sine wave. It's never gonna be able to pass this threshold if there is no additional signal on it. But by addition of noise, if there is some amount of noise, now we see like it's this noisy part, like when it's added with the sine wave, can possibly exceed the system threshold. And in fact, at certain noise level, we see that it will exceed the threshold. And if there is like some output pulses here, so we see like a bunch of pulses here and then another bunch of pulses here. So like we see that the period of the sine wave could be acquired. So like we can talk about the periodic, some frequency content of the signal that we are trying to sense. If the noise amount is too much, on the other hand, it's gonna be basically the signal information will be lost. So therefore, there is an optimum level of non-zero noise that will maximize the detectability of this input signal, which is normally a subthreshold signal. So there is, the term is kind of like, it's stochastic for the noise portion of the mechanism, but resonance, there is no actually like frequency resonance in the sense that we understand it, but it's kind of like not a very good naming in that regard. There is no like frequency resonance going on, but it's basically, interestingly, it was first discovered like in 1980 or 1981 when people were investigating the climate changes, like as Earth, as the world experiences like an irregular weather, a regular climate, and then an ice age every 100,000 years. So like, they have proposed that like the noise which is coming from the space, outer space, like from the sun and other stars, so that noise is actually helpful in moving the Earth's climate in one direction and then remaining and make it remain there. So like this detection can be also observed as like, can be also considered or can be also considered when we consider the movement of a particle like this particle green in a bistable well like this. So this is basically, we are talking about two states. Like in this threshold case, the state is 1 when it exceeds the threshold, and it's 0 when it's below the threshold. So in those threshold level. So we have this barrier for the particle to pass. But if the signal that is applied onto the particle is small, then it's never going to be able to pass. But by adding some amount of noise, we can make the particle move those transitions between the stable points. So you see this output performance, whichever way you assess the performance. But it's basically, it's not the maximum when there's no noise, but it's maximum. It reaches a maximum when there's a certain amount of noise, and then it decays, of course. But we applied this idea on improving the detectability of neural spikes in a neural recording from the brain, from the cortical layer of the brain. We have spikes, like we detect spiking activity of surrounding neurons. So we have tried to see like if, and the thing is like the extracellular neural recording is already coming with noise. So like we don't need to add noise to it, but it's already coming with noise. So like our idea was, is that noise potentially the optimum noise, or can we design an algorithm where that amount of noise in the existing noise is the optimum level of noise that will enhance or maximize the detectability, or that will enhance the signal to noise ratio of the spike. So we have here you see like a couple of complicated graphs, but like here on the left hand side you see like R-val. R-val is not bistable, like in this case we go with a monostable, and we have seen that like by introducing the signal onto this particle as a force, you see here in this one you see a noise-free, well, just noisy part of the recording, like this top black line, and then here we see like the spiky portion. And then we add noise on this whole thing, like this SD1 is what we are actually inputting as our input to the system, our filter. So as you can see, like the spiky portions are not even visible, like it's kind of like get lost in the noise. But our system output produces no spikes for a noise only portion, but it can detect, it can easily show like outputs as the spikes wherever there are spikes. So you see like here and here we are showing the movement of the particle. In a non-spike case, it basically remains around 0, but in a spike case, it can go like it can move further away from the stable point. The high level valve shape is shown here. And more recently, we have expanded that study. And not only we tried this valve, single monostable valve, like a shallow valve in a sense, but we have tried steep valve, bistable valve, and steep bistable valve. So this is the input. This is our input, and this is the shallow wall monostable. So in other words, this is similar to, this is the output of an algorithm similar to the one in the previous slide, this slide. But we have seen that if we make this shallow monostable not overdamped, but underdamped, and we do that underdamping in a controlled manner, we are able to significantly improve the SNR. Like here in this plot, you're seeing the comparison of different valve shapes and damping cases, damping configurations. So we are able to obtain 10 to the power of 8 or 10 to the power of 9 SNR for a spike, for a given spike, a significant improvement. You see like there is almost 0 noise, but the spike is enhanced significantly. And it's still the same valve shape, but what we do is we increase the damping around the 0, and we reduce the damping for the other parts. In other words, if there is only 0 noise only portion of this extracellular recording, it's going to be kind of like stuck in here with the high damping. But as soon as it can potentially reach to get beside that region with high damping, that now it's going to experience a low damping, so it's going to be basically rewarded by low damping so that it can move further away. So the thing is, like, physically, this solution of the particle in a well is governed by this generalized Langevin equation, and it's a second order differential equation. Here our output, the particle x on the x location of the particle is our output, and the force we apply on the particle is our input. So like our input is this noisy signal Sn, and we have the x second time derivative and first time derivative with some damping. And on the right hand side, we have this potential shape. So like depending on whatever well shape you go, so you have the first derivative of it with respect to the x. So this Langevin equation, digitally we are solving it, like all these results I'm showing using obtained using MATLAB, and we are using Runge-Kutlam method to solve for this differential equation. Physically, it's basically a matter of implementing an integrator, a couple integrators, two integrators, and multiplier and adder in the analog. So like, for instance, I mean, you have seen how we do adding in analog, like by adding some currents. So we have also, like, we can multiply currents. Currents can be in the order of picoamps, and we can multiply them and produce and obtain their output as the product of two currents. So there are like some circuit techniques that allow us to do that. And you see like here an integrator, for instance, with the use of some capacitor. And again, we are processing everything in terms of current, and potentially we can solve this. And more interestingly, physical solution of it, if the circuit is carefully designed, of course, is there's not gonna be any approximation like Runge-Kutlam method is doing. So this relies on the step size, so like it does some sort of approximations in that. So potentially physical implementation of this equation, and actually any differential equation, is potentially possible with analog implementation. And eventual goal is to implement this algorithm on an on-chip spike detection, and still like just send out the spikes, detected spikes. So considering now, if we compare this application with ECG bandwidth is much smaller, like 100 hertz, but this one is going up to 8 kilohertz. So the radio of this guy, if it was supposed to send raw data, would have worked much more. Would have burned much more power. So like any improvement here in that case is gonna be a significant improvement in terms of the power of that total system. So that's the next step, kind of like implementation of these results in analog. So I would like to talk a little bit about like another future, current and future research interest, which is implementing hardware accelerators using physical computation, using analog and neuromorphic computation. So like we all are familiar with today's computing achievements have been were possible thanks to machine learning algorithms, and a simple machine learning algorithm is an artificial neural network where we have inputs, feed forward data flow, and we obtain output, and then we have also some training from the error calculated is back propagated towards into the input, and the weights along the route is updated. So the thing is, like, if we consider today's digital processors, such as like a CPU, what we see is like we suffer from memory bottleneck, which means basically our processing speeds, like our CPU consists of a processor, like basically a control unit and ALU, and then it has also a memory unit. So the data flow between the two is the speed of data flow is slow. So no matter how fast your processor is, so you're kind of like limited by that data flow. And that's kind of like a problem in considering if you're using CPU to implement a neural network, because like if you look at this neuron, like whose job is to receive the output from the previous neurons and multiply them with some weights and then add them up and then implement some nonlinear function. But if you look at that poor neuron here, what we see is like it needs to access that memory many times to receive the inputs, to receive the synaptic memory, like the weights, and then to produce when it produces its output to feed the memory with its own output. So like for this neuron just alone, we'll need like 3 sets of memory access. So it's going to visit this guy many times. And there are like digital ways or architectural ways to improve the or reduce that memory access bottleneck, or von Neumann bottleneck. Speeding up the bus line or leveraging registers at the CPU are all things that have improved that speed significantly. Or using multi-cores is another thing. So the thing is like, there is a fundamental problem with implementing machine learning algorithms on general purpose processors, which is these general purpose processors are really good in implementing complex control flows, which is beneficial for conventional rule-based computing. In evaluating an artificial neural network or most machine learning algorithms, let's say, however, little control is needed. The major portion of the computation is data flow. In other words, the way that the data is going to flow is kind of well known, like which way this data is going to flow, which neuron is going to stop at. And each neuron's job is also very well known. So like there is not that kind of decision-based computation that needs to be done, which is what CPUs are famous for. So GPUs, like which contains hundreds of cores, as opposed to like a few cores of CPUs, can improve the speed and improve the speed of the calculation by performing all these computations in a distributed manner. So or FPGAs, like field programmable gate arrays, which consist of arrays of programmable logic blocks. So and each of these blocks have their own memory, and they have distributed block RAMs. So implementing an algorithm on an FPGA makes more sense than implementing it on a CPU. There are also digital ASIC accelerators, and their way of improving the latency and energy consumption is they reduce data movement. So they basically reduce the number of times the processor needs to access the memory. So that's what they do with different ways. And they also do scaling precision. So like they implement, they train an algorithm, and then they say, okay, maybe I don't need this much precision. So like they now go with, like, instead of 16 bits, they go with 12 bits and see that the result is still equally or very similar. So they go with that. And then they exploit the sparsity of the network. So memory access is not only problematic in terms of latency, but also in terms of power consumption. So you see like different energy costs of register file or inter-programming element communication, or on-chip buffer or off-chip DRAM. So like you want to definitely minimize the number of times you visit a DRAM, off-chip DRAM, but you also want to minimize the number of times you go to the on-chip buffer. So you want to take care of pretty much everything within these two, register files and inter-PA communication, so that you improve your power performance. So like I said, in ANN applications, data flow is often fixed. Input data will follow which neurons at which order are known already. Therefore, designer has control on how to optimize the data movement and memory access. So there are different approaches in the literature that target to reduce data movement. So one of them is the large matrix multiplication problem. So matrix multiplication is fundamental in implementing a neural network or an algorithm similar to that, which is because like all of these weight products and additions can be considered as matrix multiplication or vector matrix multiplication. So what this guy is doing is some multiplication and summation eventually. I'm assuming like the nonlinear function is going to be implemented afterwards, but an important aspect and an important portion of what a processor needs to do is those multiplication and addition. And this matrix multiplication can be divided into smaller problems so that each chunks can be revisited like within the processor without having to go to the external or even on-chip memory. So another way of data movement reduction is going with spatial architectures where each programming element has its own logic and memory and exchange information with other PEs. And so like a good example of this is Google's tensor processing unit. So it's a digital algorithm, this digital hardware, but it's basically using this algorithm family called systolic array to perform the computation. So they designed this hardware like I think within 18 months or something, but the algorithm they are using is also from 1980s. And what they do is they store the weights locally at each programming elements, which are not shown explicitly here. Inside of here, we have a bunch of, all of these rows and columns are filled with programming elements. Each of them have their own weights. And then to obtain the correct computational results, the input to each row needs to be properly arranged. So this calculation can be like visualized right here. So rather than each programming element, after producing its output, accessing a memory, what they do is they feed the result to the next one and to the next one, and also this way as well. So like they are hardwired such that not at time is equal to 1, but at time is equal to 10, or like you see here, time is equal to 13, the outputs are ready, like the matrix multiplication is ready. And it's basically leveraging the fact that each of these PEs can forward the data, and therefore there is no need to store the data at an external memory. So it allows high throughput computation, and like here you see like a bunch of numbers comparing CPU with GPU and TPU. So predictions per second done by Google's TPU is 225,000 as opposed to these smaller ones. For different algorithms, you see like the performance. So another way of improving the power, like I said, is the scaling precision. So an approach is designing a full precision well-trained neural network, then the precision is swept until the performance penalty that can be tolerated is reached. And lastly, sparse connections. So again, the architecture is designed fully connected like this maybe, and then it turns out some of these weights are not important at all. So like the architecture its density is reduced. And also like if a nonlinear function of ReLU function is used, like 40 to 50% of neuron activations, neuron outputs are going to be 0. So like it's going to be, those weights are not going to be, those weights that take these as the input won't be important in that case. So this is where I would like to come to. What we have seen so far is basically all digital approaches. And there is also like this kind of neuromorphic approach, which is resistive crossbar arrays and neural network hardware based on emerging non-volatile memories. So even in the TPU case, the data is delivered in a serial manner. But here we see like you see only like 2 by 2 array. But what we have is like our V0 and V1 as our input, and we are implementing this function, like this matrix multiplication, vector matrix multiplication. So what these resistors are, these are just resistors. What they do is like they can store some memory. They can store their resistance value. And their resistance value can be programmed, in an efficient way. So in a way, like they are potentiometers, but they can store their resistance values, and their resistance values can be increased or decreased. And that will be like that resistance value will be serving as our weights in our neural network. So what this guy is doing is like, if we see like here V1, so and this voltage is maybe 0. So like this resistor sees a V1 voltage drop across it. So its current is going to be its conductance, which is 1 over resistance, its conductance times that V1 voltage. And that current is going to flow this way. And it's going to be added up with the current coming from this guy, V0 times G00. So those two currents are added again, like the way that I've shown earlier, as a KCL node, and that summation doesn't add any burden on it. And all of these computations can be done at the same time, like simultaneously. So while providing the input, we already obtained the output. So this is massively parallelized computation. The problem here is like implementation of this guy, like this non-volatile memory. There are like memristors, the different memristor types. The name, as the name implies, it's a resistor with memory. So there are ionic memristor, phase change memristor, spin-based like magnetic memristors, and they all come with their own problems. So they are, in a sense, like they are basically, again, like in artificial neural network terminology, they're storing the weights. But from a biological synapse perspective, they're storing the synaptic strength. So you see, like we have an input, we have an output, and the inputs affect how much the output is affected by this input is determined based on how strong this synapse is, how much the synapse can be populated by ions or neurotransmitters, and how many receptors this receiving or postsynaptic neuron has on it. So like that weight determines how much input can affect output. So it's kind of in a very scalable manner can be implemented using those memristors. And we have also another type of device, floating gate transistor, which I am more familiar with and I have used previously. So this is a floating gate device where we can control the amount of current for a same input by increasing the weight stored in that. So we can increase it and decrease it and increase it, decrease it. But the problem here is these step sizes are really like very hard to achieve, like a very to achieve a single step size, and not the current levels. Like if I increase the current, it's it's easier to control the step size to be equal for each step. But that's one thing. Another thing is we have a limit at the maximum amount of weight that it can store. And another thing is like this way and going back, it's not symmetric. So like different numbers of pulses need to be applied to change the weight stored in this device. So existing material-based, be it a CMOS, fully CMOS compatible, or not, like more exploratory memristors, phase change memristor or so. So they come with those problems, like non-idealities. So my current interest, one of my current interests is implementing a fully CMOS compatible non-volatile memory. So and my goal is not actually like I'm not targeting this time sensor nodes, but I'm targeting more like neural network training hardware, like hardware accelerators, where the goal is to reduce that latency, where we want to train like huge amounts of data in a fast way. So in that case, we are not too much worried about the power consumption, but we are talking about latency and also the endurance of these those memristors. So like the endurance is basically how many times you can program this. So for this floating gate MOSFET, it's really bad. Like only after 100,000 times, it's gonna degrade. For these, like some of these MRAM, you have like 10 to the power of 16 for STT RAM. And so you have much better, but still like if you consider like huge amounts of data being training some neural network implemented using those non-volatile memories, still that much endurance might not be enough. And high precision and symmetric updates are going to be helpful. So you see like an exemplary study from not my research, but IBM. They use basically a very rudimentary kind of like storage on a capacitor, like it's the basic analog storage, but they are programming it with some current sources implemented using P3 and N3. So they increase the voltage on this capacitor and decrease the voltage on that capacitor, and that voltage controls a resistor. Like this device acts like a resistor, so that resistance can be controlled by this voltage. And they have shown like a very nice, but these are simulation results again, so they have shown like nice increase and decrease. But once such a CMOS device can be implemented, like that we can really in a very fast manner, we can change its weight, its resistance. It can be very helpful in training of neural networks. So I'd like to stop here, and thank you for your attention.
Thank you very much, Dr. Toreyin. That was excellent. Excellent talk. I had a question about the ODE that you're solving.
Yeah.
We have now, tiny FPGAs with hard neural IP cores that are capable of like 1 milliwatt inferencing. I was wondering, have you considered solving the ODE using a solver, which uses like a continuous depth model? There's a famous paper by Ricky Chen of Toronto where he shows how to compute gradients using an adjoint sensitivity method, and it solves an ODE backwards in time using a neural network.
Oh, that's very interesting. I wasn't aware of that actually, and I would be very interested in. So we have a tiny FPGA, you said, that can implement that neural network.
Yeah, I can send you a paper.
Really, yeah, if you can send it, that will be really good. Yeah, I wasn't aware of actually like this Rangekutta method. I mean, I can only use MATLAB honestly. So that's kind of like the only software that I'm most familiar with. So right. Whichever way I find that MATLAB uses, I went with that, with not having another method to solve that in mind. I didn't have that in mind, so I didn't look for anything like that. But if there is another way of solving the equation and effectively, that would be really cool to show it also.
Yeah, I had another question about, you had a slide a while back where you used noise to estimate signal frequency.
Yeah.
I was just curious, how sensitive is this method to, or since thermal noise is, 10 log 10 of KT?
Yeah. So like this background noise, I mean, it's going to be really like either be white noise or, I mean, a combination of white noise and a colored noise, most probably. And I mean, like what is important is the intensity of the noise, and that intensity is determined, that optimum intensity is determined based on how small your subthreshold signal is, and also how what is your threshold level. So therefore, it's not really the, I mean, like, there are studies that compare different types of noises on the detection, and they have shown, like, in certain cases that colored noise can be performing better, and in particular in biological neurons, detecting the inputs from other biological neurons. They have shown that some 1/f colored noise is performing better than white noise. But it's more like, what is more important is like the intensity of the noise, whatever noise you're using. Does it help your question, or are you asking something else?
Yeah. Yeah, I was just curious. This is kind of like when you determine receiver sensitivity, and you have to factor in thermal noise. I was just curious how
exactly.
temperature affects.
That all noise sources should be taken into account. Exactly. Yeah. Like, yeah, they can change. You might need to end up adding some additional noise or not. Maybe you are already passed by that optimum noise level. So yeah, you got to be looking into that.
Okay, so I'd like to open questions up to the audience. Professor Castillo.
Yeah, this is Pat Shoemaker. I don't know if you can hear me.
Yes.
Yeah. Okay. Somebody's been interested in analog computation. Anybody that's worked in that field over the last 30 years knows that, like, these simple current mode circuits, particularly when operated in sub-threshold, tend to be really susceptible to device mismatches that significantly impact the accuracy. Just wondering if you had any comment on that based on your experience.
So that's true. So that's kind of like the, like if I go back to here. So we haven't tried our algorithm on multiple chip dies implemented on different chips. So we haven't particularly investigated the mismatches, but we didn't need to do any post adjustment on biasing, like much adjustment on the biasing after we send it out for fabrication. Like the simulation based biases that we have used in our simulations, we were able to go with them, and we were able to get the results. So I mean, there are, like you said, in subthreshold, because of the exponential relationship of current to voltage, any mismatch is going to has a greater impact on the output signal. But I think, like, that's something that we need to do, like compare multiple chips and see, like, and quantify that. So that will be easier to comment on after doing that.
Okay. Do you take any measures on these chips, like common centroid layouts or anything to promote matching?
No, I mean, those things can be done for sure. We haven't done those things. Our goal is to really, like, to demonstrate that it's possible to obtain that ultra low power and high sensitivity. But those measures can be taken. Still, like, your circuits can suffer from those mismatches.
Okay, any questions, Dr. Castillo?
Yes, this is your show, and just I don't have any questions.
Okay, how about Dr. Venkataraman?
So, Hakan, no, I was wondering, in terms of scalability, I understand the low power requirements, but still, what are some bottlenecks that this type of system poses for scalability to large, let's say you're training neural networks with very large inputs and with multi-layer things. Where's the bottleneck then?
So the bottleneck is the memory element, and that current versions of those crossbar resistive arrays, what they do is they do the training somewhere else, and like on a digital platform, and they obtain the weights and they program individually each of these elements. So that's given the fact that the fabrication of those devices are not fully developed, like they are not, their reproducibility is poor compared to CMOS fabrication, for instance. And therefore, the mismatch along the or inside that crossbar array, when you try to program each of these elements with certain weights, is going to be significant. So that's kind of like messing up when everything is programmed digitally and the weights are then programmed onto the crossbar array. But one solution that is proposed is doing the training on the chip also, like on that memristor array. So like the training will be done on the device itself rather than somewhere else. So that will take care of that primary bottleneck. But in that case, now the problem is the non-volatile memory elements suffering from those endurance, and they also like their precision is, I mean, their symmetric programming is not possible. Like they do not provide symmetric programming. So currently, the central problem is those the memory elements not being perfect.
Okay. Yeah, it'll be nice if you can make the training in situ, so then you can make adaptive systems.
Yeah, that's actually like what I mean. I know IBM is working on that, and a couple research groups are also working on that. But that requires really like a reliable non-volatile memory, potentially digitally controlled, some analog, but a seamless integration between digital and analog. But the advantage of a crossbar array should be leveraged, I believe. That's the one that's going to speed up the training.
So just out of curiosity, these resistive array memories is somewhat a revisit to the past, is it not? That is very early computers.
Resistive memory elements.
Yeah.
Actually, like the memristor was only found. Well, it was known as an element in 1970s by a Stanford professor, but it was only realized that they fabricated it in 2012 at HP Labs. So there were devices though, like all those PCMs and STT-MRAMs. Conceptually, they were developed before, but they didn't know that it was a memristor that was kind of proposed in 1970s. So it's kind of like new in that regard, really. Like there's a huge focus on doing improving the fabrication of those devices.
Nice.
Yeah.
Okay, so I'll go round robin in the participants. Does Mandy have any questions? Okay, how about Bryce? Wen Jian? Lee? And how about Raymond? Raymond, do you have any questions?
Sure, I'll ask a question.
Yeah.
I was wondering what your, oh man, I don't know why I can't get my camera to work, but I was wondering what your approach for fabrication is. Are you trying to develop fabrication facilities on campus? Or?
No, I would like to go with CMOS fabrication. Like the way that I do it is like I design and send it to a company in Taiwan. Like Taiwan is semiconductor.
Offshore.
Yeah, I do it offshore. So my goal is actually, I avoided, like even starting from my grad studies, I first started with micro machines like MEMS when I first started, but then I figured it's not for me. So I'm trying to avoid actually fabrication, and I really respect those who work in that field.
Okay. Do you have an academic collaborator that is as your access to the fab, or deal directly with?
I mean, I don't, but the circuit design doesn't necessitate it at this point, at least.
Okay. Okay.
Yeah, I don't have though.
Thank you.
Just a quick comment. We used to make use of the Moses service, and that allows you to fab with TSMC, and also there's some IBM designs.
Yeah, I used to use Moses, and for this chip and the floating gate device, I used Muse. It's also another MP, the multi-project wafer consortium. They are also pretty good. I was very happy with them.
All right, excellent. So let's give our speaker, Dr. Toreyin, a round of applause.
Thank you very much.
And thank him very much for an outstanding talk.
Thank you very much for inviting me again and hosting me. Thanks a lot.
Thank you. Thank you very much. That was great. And have a nice weekend, everybody. Thank you for attending.
Thank you. Bye.
Bye.
Bye, everyone.